Well, thank you so very much for putting me behind that presentation. How am I going to follow up that? Landon, fantastic presentation, really great use of the software. And let me take the opportunity now to show you a little bit more of what can be done with the software and help you. And really, this is not meant to teach you how to use it, but we call this the art of the possible. Things that can be done, things you may not have realized can be done with the software. And I want to share that with you. So let me come here and again share my screen. And let me open up a quick slide here. So this is what I want to cover. We're going to go over a basic, we've already talked about the first page, so we can skip that. I want to show you a couple of success stories, and they're important. And you'll notice that that slide that Landon showed at the end of his presentation, we call that a success story. And we have a number of them from teams, and we would love to add your successes to this bank that we have. And I'll tell you that a little inside secret here. Hot, as was mentioned by Landon, has used our software extensively, and these success stories that they've created, they presented them to the judges, and that is one of the reasons why they, what was it, the Excellence in Engineering Award or something like that they won, Darius? What was it? What was the name of it? Do you remember
Yeah,
offhand?
that was Excellence in Engineering at a GS.
Yeah, and when they presented it to them, the guy specifically called out that they highlighted and showed the analysis that they'd done. So this is the sort of stuff that we want to do with you, and we want to help you build these success stories that can allow us to brag about you and allow you to brag about yourself. We're going to talk about cleaning up your model. We're going to talk about SimSolid. Landon had mentioned the speed of Inspire. Well, I'm going to put that into overdrive for you. Optimization, manufacturing constraints, making sure your optimized parts are manufacturable. We're going to talk a little about something that you probably are not aware of, non-structural masses. If you want to sound cool, you can use the lingo NSM. They're going to speed up your analysis with a single button click. Being able to calculate reaction forces, so understanding how to put forces onto the model based upon analyses. And then motion-driven optimization. We'll talk about how to use our motion solver to drive optimization. You get greater accuracy with a lot less over-engineering. And then we'll talk, just wrap it up with just a brief overview of the first page, and want to talk to you about the student contest and the webinar that we did last December, I think it was. Okay, so let me move that out of here, and I have, just for speed and convenience, all of my Inspire windows open and ready to go. And I know this is not a robot part, and I apologize for that. What I'm going to do applies to robot parts, but a robot is going to have a whole lot more of these fasteners, and is going to not be able to fit in the time that I have to be able to demonstrate this to you. So what's going to happen is when you start using Inspire, you're going to get that CAD in from your CAD system. And a lot of times, every model that I've seen of a robot, they've got everything modeled in there, washers and bolts and fasteners and bushings and all that sort of stuff. And a large portion of that is actually going to weigh down your analysis. It's going to make it take even longer, if sometimes it can even run at all, because of the size of some of these. And cleaning up your parts is very, very important. Now, this can be done in CAD, and if you can get your CAD operator to get rid of this stuff ahead of time, well, then you're even better off. But in the case of Inspire, if you bring it into Inspire, so I've got this drone. I picked the coolest thing I could that wasn't a robot. And we've got all these bolts and these fasteners and all that sort of stuff in here. And the way that Inspire works is it connects all these parts together and makes sure that they're connected to each other. But that's not what we want from the fasteners. We just want the software to do it. So I can come here real quick and I can get rid of all of these fasteners. Fortunately, they're named all similar things, so I can highlight in here and grab them and delete them. And then we can allow Inspire to create its own fastener connections. That can happen automatically and almost instantaneously, and it's going to replace it with its own mathematically driven models of fasteners, screws and bolts. And then it's going to alter the contacts. You see that these are now yellow. So it's a far more accurate definition of the contact between these two pieces. It means that they're allowed to separate from each other if necessary, which forces the analysis to drive the contact down through the connection through the bolt and not through the actual bonded contacts. I know that's kind of high-end talk here, but the bottom line is by getting rid of all of that extra stuff that you don't need and then use Inspire's tools to create your fasteners, you can do it very quickly, easily, and get a much, much more accurate result out of the deal. And again, they're not getting into training here. I can absolutely do presentations for your teams to discuss that further, but that's just one of the things that we can do. Next on the list, SimSolid, and this is probably my favorite portion of this presentation. So when Landon did his analysis, he used what was known as our OptiStruct solver, and it is a very high-end analysis solver that is been utilized for over 30 years now, and it's also the solver that we do to do our optimizations. But if you're just doing an analysis, especially if you're doing analysis on a single part, it is, or I'm saying on a collection of parts, it can take a long time to do that. So let me show you what it's going to take to do this in Inspire. I mean, using the OptiStruct solver. We can check which solver it is under the preferences. In the run options here, we see OptiStruct, and we have the option between OptiStruct and SimSolid. And we'll talk about SimSolid in a second. But let's try it the traditional way. So I'm going to pop this up here on the screen, and I'm come here to analyze. And I'm going to say, okay, analyze. I want to run this, and we'll start the timer now. Now, what's happening in the background is it is going and it is modeling this up. It's meshing this up, not to go too deep into finite element analysis. It's breaking this up into a whole bunch of little pyramidal pieces. And with all of these parts on here, and most importantly, the thinness of all these parts, it's taking a tremendous amount of time to do that. And it's going through and it's setting up all of the behavior of this. It's modeling up the forces and what's holding it in place. And this can take a little bit of time. And it actually will take about 30 more seconds. I did test this in advance. It comes in right around a minute and 15 seconds. And keep in mind that this is just the pre-processing of this. And this isn't meant to downplay the importance and the usefulness of OptiStruct, but to let you know that in a situation like this, this is not the ideal part for OptiStruct to be analyzing. When we have a big assembly like this, SimSolid can do it much, much faster. And we should, I think, hopefully I've timed my speech here to just about the right time. We should be just about ready here. And it's going to pop up, hopefully really quickly here. There it is. So 1 minute and 18 seconds. And actually, it hasn't even started the analysis yet. It's actually identified some problems with the geometry. And they're not difficult problems. We can actually continue ignoring them, but it's not going to be the perfect, most accurate results possible. We can fix them. And if you've got good, clean CAD, hopefully you won't run into this. But if I click continue, you say this analysis is going to run for more than 15 minutes. It's actually a little bit over 20 that this ends up taking to run. And that's not something that you want when you have to be continually testing things over and over. So let me cancel this. I don't want to run it in using the OptiStruct solver. And I'm going to come back here to my preferences. And I'm going to switch this to our other solver in here, SimSolid. And SimSolid is a geometry-based solver. It's revolutionary. It's the only one of its kind right now. And it's in a lot of ways the future of analysis. So let's start this again. I'm going to come here to analyze. And I'm going to click run, and then I'm going to come here to this, and I'm going to start this timer right here. And now what's happening is it's sending it to our SimSolver solver. That sounds weird. And it's running the analysis. The results will be exactly the same that you got if you were to run it in OptiStruct. But, oh, look at that. It's done. Now, I didn't click it in time. 17 seconds. So Landon told us it took 3 minutes to run an analysis. That's great. I ran this on, I don't know how many parts, 20, 30, 40, 50 parts in here, 17 seconds. And I can take a look at the results, and they're doing exactly what I would expect it to do. I can even come in here and animate them. This is exaggerated animation, but it allows you to see that. SimSolid SimSolid solver, way too much alliteration there. SimSolid is a great tool to speed up your analysis. This isn't meaning that OptiStruct doesn't have a place. When we get into optimization, it's absolutely what you want to and need to use. But for quick analyses, and especially analyses on thin parts, on parts that have a lot of geometry or a lot of individual parts, assemblies that have a lot of individual parts, or on geometry that maybe just isn't the best with overlapping and intersecting parts, SimSolid can handle all those and give you an analysis result on this in 17 seconds. Okay, so let me stop this and moving right along. Come back here to my list here and we'll come to number 3. So optimization, manufacturing constraints. So this is a part, actually a part that Hot gave me to do optimization on. They did optimization on this. Let me turn this off and I'm going to come back up here and I'm going to show you how they did that. So they modeled in this big area, and what optimization does is it determines what of that is necessary and gets rid of the extra material. But if you were to just do it on its own, you'd end up with a part that looks like this. And once I added geometry to that, it looks a little bit like this, which is a pretty cool looking part. But it's also a very complex part. In fact, to 3D print this, you've got a lot of overhang. There's a lot of support action going on in there. Sure, it's the best possible, best, most optimized part. But just because it's the best, most optimized part doesn't mean it's the best part for us. We have within Inspire what we call manufacturing constraints. And what they do is they guarantee that the ultimate optimized part follows some certain restrictions and requirements. And in this case, I'm going to put on here what's known as an extrusion constraint. And what that does is it makes sure that there's a constant cross-section going through here, that there's no overhangs or little holes or cavities or caves. And we end up now with an optimized part that looks like this. This is substantially easier to either manufacture if you want to use standard manufacturing process, CNC machining, or laser water cutting, or 3D printing as Hot did. We've now essentially eliminated all overhangs and made this part a whole lot easier to manufacture, and still made sure that it maintains all of the requirements that are necessary for our job, for our analysis. The restrictions that we put on there, it's as stiff as necessary, it's as strong as necessary, but it meets our manufacturing requirements. Okay, next up for BAT is that non-structural mass that we talked about. So I've got this right here, another robot part. This actually is an arm that came from a first robot, left the rest of the robot off. And our motion, in case you haven't seen our motion is really cool. What we can do with the motion analysis is actually simulate the behavior of this. So I can make sure that everything's going to work fine, but I can also use this to drive analysis. So say I was very interested about the stress in this member right here, and I want to analyze that. Well, the more complex the motion analysis, the longer that analysis is going to take. So what we can do is something called a non-structural mass. This cage right here, this intake, to analyze a force here, or in fact, we'll take a look at the forces there, or to do an analysis on this, I really don't care about the complexity of this. All I care about is how much it weighs. It's some large lump of mass hanging off the end. So very easily with Inspire, what I can do is I can actually get this into an orientation like this. I can drag a little selection window, select everything, right click on it, and say convert to mass. What that does is it takes and checks the mass of every single one of those parts, finds out what that mass is, and then calculates exactly where the center of gravity of that is, and just puts what we call a lumped mass or a non-structural mass. A ball that has the exact same mass, and actually it doesn't even exist physically, it's just a mathematical representation of it. And I can very easily say, okay, now I want to connect this to where it's supposed to be connected in here. And now come and run my motion analysis. And it will behave exactly the way it did before. But I don't have to worry about all that geometry on the end, tying up the analysis or making the motion analysis run longer. So a really easy way, one single button click, highlight and a button click to replace a large chunk of parts, assemblies, with a mass when the actual details are not important. This is used a lot in real world engineering. I guess not that you're not real world engineering, but in industrial engineering. Now, along that, and this leads into my next topic here, automatic force calculations. One of the great things about the motion analysis is it automatically calculates reaction forces. So I can just come right here, turn this on, indicate I want my reaction forces. Let's turn off the torque so as not to muddy the situation. And let me pause it. And you'll see at every single one of these joints, it's telling me how much force is acting on that joint and in the direction that it's acting. And I can include the torques if I'm interested in those. And most importantly, it's going to change so it's constantly analyzing it through the entirety of the motion analysis. And so at any angle, at any orientation, I can check those forces. I can use them to do an analysis or just find out what those forces are so I can be aware of it. Which, and it was planned this way, transitionally leads beautifully into the last of the demonstration topics I have, which is motion-driven optimization. Actually, let me pause this so it's not taking up memory, and we'll grab my last model here. So motion-driven optimization. This is an intake from a few years back. And this part right here was critical. It's what kind of ties in both of the arms that allow the behavior. You know, if I want to take a look at the motion of this, there's the motion of that. And I modeled this with Inspire, brought in the geometry, cleaned it up as we showed earlier, and then allowed it to automatically put pivot joints and all that sort of stuff in there. But now I want to analyze this part right here. I want to optimize it. I want to make it the minimum amount of weight possible. So what typically happens is you'll come here and we'll do this. And it will, oops, that's not what I want. Oh, because I grabbed the wrong thing. The original, sorry, let me come here. This is what was done initially. This was their initial attempt at optimization. This wasn't done analytically. This was just done, okay, I'm going to connect every single point that holds on to something, and I'm going to create the kind of this truss structure. And it's great, and it worked fine. You see each one of them, there's two on there, weighed little over 1 1/3 pounds, 1.372 pounds. And that's fine, and it worked. But if we take optimization and instead use the motion to drive optimization, what I can come up with is this. And you'll see this weighs 0.963 pounds. So almost 0.4 pound reduction in mass. And it was driven by a motion analysis. And the reason why that's important, if you remember back to the last thing I showed, those forces are continually changing direction. So I can't pick a single one. I can't say, okay, it's a 5 pound force in this direction. That's going to change throughout the thing. So this is more accurate because it drives the optimization by looking at everything that's going on through the entirety of the motion. And then I just did a quick analysis on this, and you'll see the results change through the, it's a little slow coming up probably because I have so many other models open at the moment, but you'll see the stress and the behavior of this part change through the entirety of the motion analysis. There we go. And if I run this now, you'll see stress changes because the forces on this are continually changing. So not only can I optimize it to make sure it takes into account all the possible different forces, I can then analyze it to make sure it's good. And it's showing up red here. It's only because I I brought this down a little bit to add more color to it, just so you could see the behavior. This part actually is fantastic and sees very little stress because of the fact that it was optimized through the motion analysis. So that's it for my demonstrations. Hopefully you got an idea of the capabilities. I know that we said we didn't want to talk about all of the training on it, but just what can be done. So to wrap things up, if we talked about the first page, just remember, please take a look at that first page. It's a great place to get the material. It's closed right now. We ended right now, but we had a student contest. We will be having another. It ran for a year. First prize every month was $750. And if we come here and take a look at the month of June, you may or may not recognize this guy. He is Colin Dagg of, yes, you predicted it, the hot team. He won first prize. And then following up in September, Lorenzo from the Goon Squad also managed to nab a first prize with their excellent optimizations. So we will be announcing one coming up sometime later on in this year. Once we do, you're doing your work already. Utilize that and take a look at our contests. And then last but not least, coming back to the first page, we did a webinar in December. This is the recording of that webinar. Take a look at it, and you'll find a bunch more information and some other success stories. So.